In this video, I will show you how to find the exponential model by undertaking a doubling time and half time process. The doubling time exponential model can be computed as follows. Suppose xt equals a times b to the t's power for b greater than 1. Because this is an exponential growth, that's the reason the base is greater than 1. We will choose an arbitrary time t1. Then xt1 equals a times b to the t1's power. We want to calculate the time t2 so that xt2 equals 2 times xt1. Therefore, xt2 equals a times b to the t2's power equals 2a times b to the t1's power. So we get b to the t2's power equals 2 times b to the t1's power. Both sides we divide by b to the t1's power. You will get this. So we have b to the t2 minus t1's power equals 2. Both sides, when we take a natural log, you will get t2 minus t1 equals natural log of 2 over natural log of b. Suppose doubling time t equals t2 minus t1. Therefore, doubling time t equals natural log of 2 over natural log of b. So b equals e to the natural log 2 over doubling time's power. For exponential decay, we will use half-time process instead of doubling time process. You will get the b equals e to the negative natural log of 2 over half-time's power. For the data of world population size from years 1960 to 2002, I will use the initial value 3.03. Doubling time, we need to figure out in which year it is 3.03 times 2, that is 6.06. It's here. When x equals 39, since the data of world population is exponential function, we got to use this doubling time equation. We already got the data for doubling time. That is 0, 3.03, 39, 6.06. Then we put into this equation. For this t doubling time, it is 39. Therefore, b equals 1.018. Use x equals 39, y equals 6.06 to substitute into this function. You will get a equals 3.02. Then this will be the exponential model. Then we can put this into decimals to check how well it fits the data of world population. Now we put the function y equals 3.02 times 1.018 to the x power into these decimals. Then you could see how it fits the data of world population. Then you can download the image and copy paste to the Word document. Now you get the figure 5, y equals 3.02 times 1.018 to the x power and the data of population. Now we got 3 different exponential models by using 4 different methods. Then we need to compare which one is the best fit. We got to use SSE this time. SSE is the sum of square residual error. That is an unexplained variation. Instead, we often meet with the SST, SSE, and SSR. SST is the sum of square error total. SSR is the sum of square regression error. This is explained variation. SST equals SSE plus SSR. Suppose this f of x is the regression line. So we have SSE equals the sum of original data minus the expected data squared. Then for this SSR equals regression data, that is expected data, minus mean square. For SST is the sum of the original data minus mean square. Then for R squared equals SSR over SST equals 1 minus SSE over SST. When we have a correlation coefficient R equals 0.7, then R squared equals 0.49. And it implies that 49% of the variability between the two variables have been accounted for, and the remaining 51% of the variability is still unaccounted for. When SSE decreasing, then the R squared is increasing. So we will compare these 3 exponential models by calculating the SSE. I use Excel to figure out SSE. Then copy, paste this table to the Word document. Here is the table we copied from Excel. Let's check the sum. 5.53, 1.65, 6.66. So we can draw the conclusion. Y equals 3.19 times 1.016 to the x power has the smallest SSE value. So y equals 3.19 times 1.016 to the x power, given by transformed linear regression line, is the best fit for the data of population.